Hello everybody, Dr. Schoffers here, helping you work your way through chapter 19, which focuses on aldehydes and ketones. Both of these are carbonyl compounds, so we have in common a carbon-oxygen double bond, and we'll have to further analyze this. Before we get started, I inserted a new slide that basically includes many of the highlighted jargon at the end of the chapter. As with so many other chapters, we'll have to discuss structural properties and nomenclature, how we come up with the name. There are IUPAC and common names. There are certain physical properties to understand, especially when it comes to mechanisms. We can prepare carbonyl compounds through oxidation of alcohols, and there are different types of reagents possible. We can also utilize ozonolysis reactions that were discussed in Orgo 1, as well as hydroboration of alkynes. So a significant portion here is actually review of material you already encountered in Orgo 1. So now we're seeing the opposite or the other end of this aspect. The resonance form of carbonyl groups, understanding where the electrons are and how this carbonyl group will interact with protons and with nucleophiles is going to play an important role. We'll have to see the patterns that happen in the many transformations in this chapter, such as the nucleophilic attack on the carbonyl group. We have hydration of alkynes. This also involves keto-enol, tautoisomerism or tautomerism, formation of cyanohydrates, hydrates, hemiacetals, acetals. And I'll tell you already that a lot of material, or some material in this chapter, will be important to succeed in chapter 24, which focuses on carbohydrates. We also look at mechanisms for cyclic acetal formation, and then there are nitrogen nucleophiles that can lead to imine formation, shown here, and also enamines. There are hydrozones from hydrazines, oximes. There are some named reactions such as the Wolff-Kishner reduction, the Wittig or the Horner-Woodward-Emmons reaction. We have to understand a fairly new kind of unusual structural component, which are termed ylids, and it will be beneficial for students to work the mechanisms. There are also specific intermediates such as betaine and oxophosphate, and some more at the end. An oxidation procedure, the Baeyer-Willige oxidation that can lead to lactones. We'll talk about migratory aptitude, and then spectroscopy, how we can analyze these compounds. Let me start out with, and you can pause the video at any time as you're taking notes. Sometimes it helps to look at what lies ahead, and here's just one of many schemes presented in this chapter and in subsequent chapters to help us understand, and there's a typo here, I'm sorry, this is chapter 19, to help us understand what's going on. I also recommend that you are being very cognizant of all the material that was covered in chapter 3, and that is the acid-base chapter, because the mechanism and the transformation will vary based on whether we're dealing with acidic conditions, which I'm circling here with red. Here's an H+, so that all means acidic, just to show you, and you can see there are many of them, and maybe I'm not going to try to do all of them, but then there are also reactions that are utilizing basic conditions. That would include, for example, the use of lithium aluminum hydride, also abbreviated as LAH, as well as the use of a Grignard reagent. Those are the reagents that have a magnesium in there. And then we have also a Wittig reaction. So there's a whole host of reactions coming at us. It sometimes helps to look at the end of the chapter to see where you're going, right? So what your goal is. And here I've formulated this as well. So in every chapter, we're basically looking at concepts and vocabulary. You are truly learning a new language. It might sound nerdy. The technical jargon is part of thinking like an organic chemist, and I'd like to utilize some of these aspects when you do your Mathias point discussion. Are you using the vocabulary? Are you really being, are you assessing what needs more attention in your learning as we're going through this. And then also at the end of the chapter, we have a summary of all these skill builders component. And I've just cut and paste some of these in the current chapter 19. And as we're looking at this after nomenclature, it's going to be about mechanisms. Products for hydrolysis. Mechanisms can be very helpful too. Hydrolysis reactions are very hydrolysis reactions do play a prominent role in here, and that's one of the learning outcomes. And then also, what is the major outcome of some named reactions, and then to look at that with a synthetic aspect. I understand that students often feel overwhelmed at that part, but I want you to know that if you have some challenges and if it takes you a long time, it may be that you need to review some of the concepts you may have forgotten about in chapters 2 and 6, but also in here chapter 3 for acid-base chemistry. As I'm going through this lecture, I hope you get some useful information out of it. The purpose is not for you to jot down everything that's on the slides, but to prioritize and to highlight and summarize and paraphrase, which is part of the learning mechanism. And of course, if your pencil isn't moving, you're not learning how to draw structures, assess structures, and manipulate structures, or understand which bonds are formed or broken, and what some of the functional group interconversions are. So moving on here, talking at the very beginning of the chapter, and you can always pause this video to jot down some notes. Again, it's not about that you should copy everything. I have seen some students doing really well with submitting, let's say, 10 pages to summarize a chapter. Some of the chapters are longer, some of them are shorter. I'm not discouraging from writing more pages, but you are also in charge of assessing what helps you most. And as we continue, as you get to the next test and then to the final exam, which is cumulative, what helps you really succeed in and show that you've learned this material. So as we're looking at ketones and aldehydes, they both have the carbonyl group, the carbon-oxygen double bond. Here we have a hydrogen. In this case, we have an R group. These R groups can be the same or different. It could be R1, R2. Important in both biology and in industry are two very simple carbonyl compounds in this chapter. The simplest aldehyde is formaldehyde, which is used to preserve materials. And, it does help to understand the bonding pattern, the valence, and which kind of electrons are available. So I do like to draw in, especially when there's a reaction on that functional group, to draw in all the electrons so I can understand the complexity of possible reactions and the outcomes. The simplest ketone is acetone, and it's actually used as a solvent, especially in the laboratory after doing a reaction to get rid and clean the glassware. So acetone is very helpful. As we're looking at the next slide, again, you do not have to copy down every structure. Maybe you want to, write down some names if that helps you. For us, organic chemistry is about pattern recognition. What do we recognize? Vanillin has an aldehyde group. Cinnamaldehyde has an aldehyde group. Carvone is a ketone. Benzaldehyde is a benzene ring with an aldehyde. When we look at steroids, basically very powerful messenger molecules. Here are two: progesterone, associated with the female body, testosterone, predominant in the male body, although women have testosterone as well. Here we have a ketone functionality in the side chain on the 5-membered ring, and here we have a ketone functionality on a 6-membered ring that actually happens to be conjugated, right? We talked about conjugated systems. In testosterone, here we have the ketone in conjugation with a double bond. So know that these are common bonding patterns that we can encounter in nature. And the biology and medicinal chemistry and pharmaceutical chemistry can all be linked to some of the basic chemistry aspects. On the next slide, I inserted, so we have ketones and aldehydes. There are many other examples, and as we are heading towards chapter 24, which is about carbohydrates, I wanted to just make a couple of notes. Glucose and fructose are both very sweet compounds. They actually belong into this category. Right now, we're looking at simpler ketones and aldehydes. Once we get to glucose and fructose in chapter 24, those are very functional, rich molecules. To give you an insight into this, I'm going to switch over to my ChemDraw application. It is set up such that I can just type in a name and I can ask it to now give me the structure. It's preloaded. And here we have a structure for fructose. Let me do this again. I'll do this the same for just saying I'd like to get a structure of glucose. It saves some time to put this together. So here are two representations. A couple of notes. Number one, here's your aldehyde group in a glucose. Here's your ketone group in fructose. There are lots of hydroxyl groups. Hydroxyl, 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 hydroxyl. And these are both C6 compounds. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. When we get to chapter 24, I will teach you how to remember how to draw these two functionality-rich molecules in the proper way. It turns out that looking at this representation here with stereo view, so stereochemistry will show up again, especially in chapter 24, carbohydrates, and later on with amino acids. So we'll have to use some of the Orgo 1 skills. It's really important to be able to scan these structures, but this is not a good representation of these two structures. Chemists for a long time have come up with a different convention. And so I'm going to grab a template tool here where I will look up what is called hexoses, because we have 6 carbons. And under hexoses, we want to use the Fischer projection. So this is already heads up. We're going to get into Fischer projections. And here I can pick for glucose. Here is what the structure looks like. Let me do this again. I'll go into my template box and I look for my hexoses and I want to pull up the Fischer projection. And we now find, hold on, oh gosh, I can't believe this, fructose, I can't find it. Let me just say, I'm gonna construct this, and I will teach you this in the chapter 24 as well. I'm gonna copy over the structure here, and basically what we're doing is, so we have 2 molecules of glucose. There's one significant change. Number one, both of these are Fischer projections. The way glucose and fructose differ is in the oxidation state in C1 and C2. So I'm going to get rid of this hydrogen here and or this bond here. I'm going to increase the bond order here. So now we have a ketone, and this group here will actually be a CH2 group. So I'll just copy that over. All right, here we are. We have 2 Fischer projections of D-glucose and D-fructose. The Fischer projections help because we don't have the clutter of a zigzag line. And here we have the Fischer projection, and the stereochemistry is represented by placing a group on the left side or the right-hand side. Okay. So there's a lot of chemistry that's coming towards us, but I just wanted to point out how we can look at now these 2 sweet molecules. And there certainly has been a lot of debate when it comes to nutrition. I actually also last year published a chapter on the chemistry of nutrition, putting chemical molecules at the center as to what it takes to have or to promote a healthy diet in the body. Let's go to nomenclature. This is fairly straightforward. You can pause the video and think about some of these compounds. I'm going to promptly walk through them. For aldehydes, when we have a parent chain, we're basically replacing the E with an AL. So butane becomes butanal. And as we've seen before, when we have a parent chain, we need to include the carbonyl group. And where the carbonyl group is plays an important role. On the next slide, here we now have the example. Here's butane, 1, 2, 3, 4. Here's butanane, 1, 2, 3, 4. And at the end, there's a carbon-oxygen double bond and a hydrogen. That's your typical aldehyde pattern. The parent chain must include the carbonyl group. So as we're looking at, for example, here is a regular carbohydrate, no functionality, it's just carbon-carbon and carbon-hydrogen bonds. So this is an octane, the longest chain. If we are to add now an aldehyde group, we would have to include this. So now the parent chain becomes a hexanal, and all of this is treated as a substituent. As we're looking at this, now we need to give the carbon-oxygen double bond the lowest number. We've seen a similar phenomenon before when we were learning about these structures. So the CO is given the lowest number possible. If I start on this side, it would get the number 5. If we start from this side, it gets the number 3. Okay? We have two options to integrate the functionality when we're looking at now this ketone. We show the position, which is a 3, and that would be a heptanone in the structure, or heptan 3-one. Aldehyde next to a ring is named as a carb aldehyde. Basically, we're adding something. So I might have a ring, or so let me just jot this down, and then it would be a CHO. Remember that this is a valid abbreviation for having the aldehyde functional group as shown here. And then we simply add carb because we're adding an additional carbon to the ring, and aldehyde. Okay. Moving on to the next slide. Here are some other IUPAC recognized common names as well as parent names. Formaldehyde, acetaldehyde, benzaldehyde. IUPAC is the generally accepted convention for naming compounds, so that if somebody in China looks at a structure, and somebody in Germany, and somebody in the US and California, if they don't have a visual cue, although we can easily do this now with virtual meetings, we know what these names stand for or how to name a structure with this convention. Formaldehyde is the simplest one. This only has one carbon. Acete, this is something that will show up also in chapter 20 and 21, carboxylic acids and the derivatives, as well as some of the enolate chemistry and carbon-carbon bond formation reactions. Acete typically indicates that there are two carbons. Here we have two carbons, and it's an aldehyde. Okay. You may also think, okay, a look ahead to chapter 20, carboxylic acid, acetic acid. Acete means two carbons, and it's a carboxylic acid. Benzaldehyde, we have a benzene ring and the aldehyde. And you can, of course, practice this. And as I've encouraged our students many, many times, please include just a couple of problem-solving examples. Look at some of the homework as you're doing your reading through the textbook. So how would you provide the names for these three structures? You can pause the video here. Think about it, what you need to do, and then solve for the correct answer, or deduce for the correct answer with everything we just discussed. This, of course, is highlighted in chapter and end of chapter problems. So your skill builder will stress some of the important skills that to solve for a problem. So this is just about nomenclature as we're moving on to the next slide. Here we are. Instead of writing CHO, here's your aldehyde. We don't have to show the hydrogen, but the hydrogen is there. You can jot that in. You do have some flexibility. We also have a hydrogen here. And we have two carbonyl groups, and then you can work your way through this. So this is a hexanal. 1, 2, 3, 4, 5, 6 is your longest, your parent chain. You may want to circle that, highlight it, use colors. Here we have a cyclopentane ring, and then a carb aldehyde, carbon adding another carbon. And here we have a dione, 2 times a carbonyl group. They are in a 1,4 relationship. Of course, we could also have a 1,2 as well as a 1,3, but this is the structure I drew. Please also note that stereochemistry might come into play. Here we have a chirality center, a stereocenter, a stereogenic center. There are many different terms being utilized to describe stereochemistry. You may want to draw the hydrogen or not. It's not necessary. But the types of substituents that are introduced here will actually lead to stereochemistry with R configuration. The next few slides are about a number of reviews or a number of sections that are being reviewed. We're going to quickly move through them. Again, you can pause, jot down some important information as we're moving on. Here's a reminder that aldehyde preparation was already covered in chapter 12 when you learned about alcohols. There are different conditions, PCC methylene chloride or DMP methylene chloride. Also, you can use DMSO, COCl2, and then a second step with triethylamine. So these are strong oxidizing reagents, and you are asked to remember some of these conditions. Important for an oxidation, we see typically one or both, one or the other or both rules as follows. An oxidation reaction increases the number of carbon-oxygen bonds. True. We have from carbon single to carbon double bond. A decrease of carbon-hydrogen bonds. Correct. There are two hydrogens here. And now we only have one hydrogen on the other side. So this is an important review. Again, you can pause and review this offline. Next, ozonolysis reaction. Ozonolysis reaction can be very confusing. It's a two-step procedure using ozone, 3 oxygens in there. Can you draw the Lewis structure? It's actually a helpful practice. I'm not going to focus on the mechanism of this, which was introduced in chapter 8 with all the many reactions. Basically, as I'm drawing a squiggly line here, this is a cleavage. These two molecules, or this double bond will fall apart. One molecule gives rise to 2 molecules. The first step is an oxidation. You add oxygen. The second step is a reduction step, DMS, dimethyl sulfide, which will turn into DMSO, dimethyl sulfoxide, and out comes 2 carbonyl groups. If we were to look at an example, what I like to do is, let's say there's a phenyl group here, and then we have our double bond, and we're going to have a methyl group here, a hydrogen here, and I'm going to put a hydrogen here. The way I like to look at these reactions, it might help you to visualize it like this, is draw everything but the double bonds. So I'm just going to jot down the same thing. I'm leaving out the double bond, but I'm leaving extra space. So I'm just going to space this out. I'm going to put a hydrogen and another hydrogen. And what the overall transformation of this reaction is, instead of a carbon-carbon double bond, each side now gets a carbon-oxygen double bond. And here we are. So coincidentally, we're getting 2 different molecules. Here's formaldehyde, and here we have a ketone. So I encourage you to visualize some of the overall transformations to track all the complexity of all the synthetic tools that we are getting as we're moving on in Orgo 2. In this reaction, aldehydes can be prepared from alkynes. This was a complex reaction. If I'm going to just copy this down here, and I'd like to explain what really matters for this transformation. As we are looking at the conditions, it says here hydroboration, oxidation, anti-Markovnikov, addition of water. Ding, 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 ding. Addition of water means it's a hydration reaction. I'm adding a net water molecule to the structural framework. How can I do that? Well, I can add water in 2 ways. And the way I like to visualize it, again, this is not a substitute for a mechanism, but to just recall how bonds change, which ones are broken and which bonds form, is if I split water into OH on this side, and then the hydrogen on this side. And what I'm accomplishing here is there's going to be a new bond to hydrogen on the internal carbon, and a new bond to oxygen on the terminal carbon. The structure that results from this would look like this. It would be a phenyl group because I'm taking 2 pi electrons to make 2 single bonds. Now the geometry will also change a little bit. What remains is a double bond. We have a new bond to a OH, and then we have a new bond to hydrogen. This is also known as an enol because it has both an ene component, I'm highlighting here, and an ol component. And that now the important piece to put together, that we have tautomerization, which means that there's an equilibrium between the enol form and the ketone form. We'll see something similar in a couple of slides. When we're looking at ketone preparation, again, oxidative method, whenever you see chromium, a bell should go off. This is oxidative procedure. The carbon-oxygen single bond turns into a carbon-oxygen double bond. And then here we see the ozonolysis again. We had seen this carbon-carbon double bond is replaced with 2 carbon-oxygen bonds. And now the main difference is that all the substituents around the alkene are going to be some type of R groups. It could be the same, it could be 4 different R groups. And now here we see something familiar again, terminal alkynes, but now for the preparation of ketones. I'd like to stress again that this is an addition of water. It's a hydration reaction. I'm going to go ahead and draw a structure again. And basically the conditions here are different. It's a one-step procedure compared to the 2-step procedures we just discussed a couple of slides ago. I'm going to make a triple bond. This is a terminal alkyne. There's 1 more carbon, and then there's a carbon-hydrogen bond. Now I'm going to add a molecule of water across the double bond. This is not a mechanism, just a visualization technique to see where bonds are formed and broken. I'm now going to add a water molecule such that the OH will add to the internal carbon. We can show out, so we're visualizing making a new bond to an OH group. 1 pi bond will disappear, and because we're also forming then a bond to hydrogen. The product that results from this, again, the geometry is going to change a little bit because we're going from a triple bond, which is linear, to a double bond. Now we have our phenyl group. We're making a double bond. We still have the hydrogen. And now our OH group is going to be on the internal carbon. And then we have the hydrogen on the terminal carbon. What's the key component here? It's our tautomerization, which means that this is an equilibrium. We now are going from, again, an ene-ol form to a methyl ketone. That's a really important point. It's a methyl ketone. Whenever you see a methyl ketone and ask you to generate it, you need to think about the acid-catalyzed hydration reaction of a terminal alkyne, and that we have mercury under acidic conditions accomplishing this job. And the last one of the review slides is what we just saw very recently in chapter 18. Remember that we discussed the many different reaction conditions that will create a very potent electrophile. In this case, the electrophile is an acyl cation, meaning that we are forming Se+. This leaving group, it's going to form a complex. We have an R group here, and here's our positive charge. And then, of course, the aromatic ring will use one of its double bonds as a nucleophile to make that new bond, and here you get your acyl group.